All right, so I told you to use a mathematical formula, so I cheated a little bit. I wrote a little piece of code to actually generate a complete graph and then return the number of edges in that graph. So to make a complete graph, I just looped through all the pairs of nodes, and if one node was smaller than the other, then I made a link between them. That was mainly to just make sure I didn't make a link from nodes to themselves. There was no reason not to make a link the other way. It would have not counted against the total, but this seemed nicer and cleaner. Let's look at what happens if you loop on all the different values of n from 1 to 9 and print n and the number of edges in the clique. A graph with one node has no edges. A graph with two nodes fully connected has one edge. 3 has 3, that's a triangle. 4 has 6, which is the square with the x through the middle of it. 5 is that sort of pentagram looking thing that we just showed a minute ago, and it continues growing up like that. So with that as our insight, can we actually write down what the formula is for a graph with n nodes? So essentially what happens is each node gets an edge to each other node, which we can write as each node has an edge to each other node. But notice what happens if we use that as our formula. We're going to count this edge, as it goes from this node to this node, but we're also going to count it again as it goes from this node to this node. So we've double counted everything. So that should be our formula, which is big theta of n squared. So let's just double check this. If we print n clique of n, which I counted by actually creating the clique, compare that to the formula n times n minus 1 over 2, you can see that it matches up perfectly. So really the answer that you should have given is this. Shouldn't have bothered with any of this creating of stuff. So now in addition to all those graphs where the growth rate was linear, we now have one that's quadratic.